All right, good to go. Well, welcome everyone. Thanks for joining us for Archive Dives with Oxen.ai. Archive Dives are deep dives into archive papers. The main motivation is simply to become smarter oxen, smarter people. And a lot of these papers can be challenging to read at first. They have a lot of fancy words and math, but challenging yourself to read them and dive deep is the best way to become smarter and understand these concepts at a fundamental level. So today we're going to be going over one of the foundational papers that everyone always references in the large language model space and building up on top of it. And that's the attention is all you need paper. It was originally published June 2017 from Google and some people at the University of Toronto, I guess I put in there, Toronto. And since then has kind of blown up and been extended all over the place into models like the GPT series and eventually ChatGPT and some other things, some other ones that we've covered in these dives before. But I think if we're going to dive even deeper into LLMs and like interpretability in these models, we might as well go back to the fundamentals and go to attention is all you need. So I did have some great recommendations on mechanistic interpretability of these models. So I wanted to kind of start a series on these things. But like I said, in order for any of this to make sense, we really need to pay close attention to attention. So attention is all you need is that foundational paper. And you've probably seen the diagrams, you've probably read blog posts and tutorials on transformers. In fact, there's so many tutorials out there on GitHub and in PyTorch. I decided to see how quickly GitHub Copilot could just write an encoder-decoder transformer model for me, and it took about 5 minutes, which was pretty fun to watch. I have a video here if anybody's interested. But all of that to say that this is not a new thing, and it's a thing that is pretty well documented at this point. I just want to dive into the diagrams from the bottom up and try to understand all of these mechanisms piece by piece, but I thought it was very entertaining. I pretty much just put in class encoder and it generated an encoder, and then I saw that there wasn't a encoder layer defined yet, so I defined the class for encoder layer and generates all the code for an encoder layer. Programmatically just continued to do that until I had the entire model. And I wrote a little function to count the parameters. All of this, I literally just pressed enter over and over again. And I ran it and it all compiled and spit out the number of model parameters. So I think maybe we could rename this paper enter is all you need. Because that's all you need to build it these days. Of course, I'm just kidding. There's a lot more engineering to do in these machine learning systems besides just designing and implementing a model architecture. And we can't just let the AI do all the work for us. Otherwise, we're never going to come up with new ideas. So I thought that was just a fun example to get started with before we zoom in. So starting with the abstract of the paper, I mentioned a lot about convolutional and recurrent neural networks for sequence transduction. And just for reference, like this was in 2017. So this is kind of like the before times were all RNNs and CNNs. So I think it's good to understand a little bit about those, but not dive too deep. I mentioned the term sequence transduction, and that just means you're trying to predict an output sequence from an input sequence with different lengths. So we'll be going over example of translation, but at a very high zoomed out level, you might have a sentence in Spanish and you're trying to translate it to English. I took this from my Duolingo lesson yesterday because I was trying to find a short example of a small sentence that was 3 words that generated a sentence of 5 words. And this is the one that I got that we'll be using as an example. And it's important to point out that attention was not a new mechanism that was introduced in this paper. It was introduced before this as a component that was on top of other architectures to solve problems with neural networks not being able to model long-range dependencies and sequences. But what was novel in this paper was a lot of the models before were very complicated, and the attention layer would be layered on top of an LSTM or these other modules underneath it. And so the title "Attention is all you need" means they're stripping away all of these other dependencies and making a much more efficient model than we had before. It's also important to note that it's not just natural language processing, but you can apply it to computer vision. So when we think about attention in text, we think about long-range dependencies like the first word of the sentence needs to be remembered to predict the 10th word. But in images, when you're doing convolutions, attention is also important to know this part of the image affects this other part of the image. And this is just a funny, like if you took this out, you might just think it's a person here, but it's a Shiba Inu. And attention had been applied in computer vision before as well. There's this fun paper called Show, Attend, and Tell, where they even visualize where the attention is looking at different parts of the model. And you can see at some points it's looking at the woman throwing the frisbee. At some points it's looking at the kid in the bottom corner. And this model was like a ConvNet and an RNN and attention all put together. So gets pretty expensive pretty quickly if you're stacking all of these layers on top of each other. So that's kind of like a little background in why they called it attention is all you need. In this specific paper, they apply it to machine translation of English to German and English to French. And they showed state-of-the-art results for 2017 after just training for 3.5 days on 8 GPUs, where some of these models would take like a month to train before. So 3.5 days is a big improvement on that. And I think there's also, it's good to note that there's a lot of different types of transformers. This one's an encoder-decoder one, or a sequence to sequence. There's also encoder only, decoder only. So this one is like a little more complicated, but you understand each component of the full sequence to sequence, you'll understand the encoder only or the decoder only ones. So let's dive into the model itself. This is the diagram that you probably see over and over again, and we're going to zoom in and zoom out over and over again on this thing to understand what each component is, because honestly, even when I look at it today, it makes my eyes glaze over. But once you zoom in and zoom out on each one, it's each step isn't super complicated. It's just the entire system put together is. So we'll start from the bottom at the input embeddings, so down here in the diagram, and the output embeddings, because they're really the same thing. So looking at the very bottom, and first, the encoder and decoder take in a set of input embeddings that represent each token. You can think of token as word, token and word as the same thing right now, just for simplicity's sake. And words in general have complex meaning that can be represented as a distributed vector of numbers. We could have a whole dive on how they're created during training or pre-training, but at a high level, you can think of like there's the word cat, kitten, dog, and houses, and they each have certain qualities about them, like whether it's a living being, whether it's feline, whether it's human. So like a house would have a low score on living being, but dog, cat, and kitten would have a higher one. Cat would have higher on feline than dog and house, etc. And so this would be an example of like a 7-dimensional word vector. And what's cool is if you do like principal component analysis or some other techniques to compress these 7 dimensions down into 2 dimensions, you can actually plot them and see like cat and kitten are really close to each other, but dog and house are a little farther away. You can also do math on them, which is pretty wild. So that's what's going to be fed into our model at the very bottom. And what it's fed into is an encoder and a decoder. So we'll start with the encoder, and we'll skip this little positional encoding for now. And we're going to be focusing on just this left-hand portion. So within there, you'll see there's a bunch of sub modules, but I want to start with what the encoder's job is as a whole. So the encoder's job is to take a look at the full input sentence. So if we're going back to that example before, la quise mucho, the encoder's job is to look at each one of these word embeddings and encode them into a space so that we can decode it and realize that la means her in this context, quise means love, mucho means a lot, etc. And this is like a very simple, just like one-to-one version of the encoder. In practice, if you tried to implement this yourself, you're going to be batching a bunch of these so that we can do them in parallel. So what the training data really might look like is you have a bunch of sentences down here, and you batch them by equivalent length of sentences. Since not all sentences are the same length, you're going to be putting these like pad tokens or words in there. So you can see this is like a shorter one. This is a long one that takes all 5 words. And then this is a medium one where you just need 1 pad token. You feed it into the encoder, you do some steps, and then you decode it. And you're also decoding 3 sentences out the other end. And each kind of word that comes out the other end is going to have an output probability that that is the proper translation. So you can think of the inputs as word embeddings and the outputs as probabilities of words. And so the encoder's job is really to process each word embedding and put it into a representation that's easy for the decoder to use in the final translation. So if we break this down even further, you can imagine you go from this set of word embeddings to a new set that's kind of sitting in the middle, and the encoder has taken those and kind of repositioned them in embedding space so that it makes it easier for the decoder to do its job. And we'll talk about why you need to do this in a second. But the decoder half of it is taking these new processed representations here and, like I said, outputting these probabilities. And it's kind of the right-hand side of this diagram here, and a little more complicated than the encoder itself, and is connected to the encoder. We'll see why that is in a second. It's important to note that the decoder outputs one token at a time when you're decoding the sentence. So breaking this down back to the simpler example, if you fed in these 3 words to the encoder, you translated them in embedding space, you start decoding by just putting in a start of sentence token, and you output I. And then once you've outputted I, you feed I back in, as well as the start of sentence token again, and then you produce I loved, and et cetera, et cetera. This type of processing you might hear called auto-regressive. So if you ever read that word, it's just kind of like predicting the next word from previous ones. And a fun fact about the encoder and decoder and the embeddings they use is, since they use this byte pair encoding, you can actually use the same input embeddings and output embeddings if both languages are Latin, because tokens are really just like subsets of words. And for example, English and Spanish have a lot of similar subwords within them. So they used the same input embeddings and output embeddings for both of those steps. The decoder has a very similar architecture to the encoder, but it also has to mask future outputs while it's generating the new ones. So if we look at this example up here, you can't let it see the full training data of the last 3 words if you've only predicted the second word. So when you dive into this diagram, there's like multi-head attention and there's masked multi-head attention. And so whenever you see the word masked, that's really just saying it's not allowing the model to look forward in time. And they do this with like a lower triangular matrix that masks out all of the future predictions. Okay, so we kind of have like high-level encoder, decoder. Within that, you have many copies of it. So in this particular model, they actually had 6 encoders stacked on top of each other and 6 decoders stacked on top of each other. And so next we're going to dive into what each one of these encoders is and what the multi-head attention mechanism is. So I want to just throw back the original diagram so we can reorient ourselves. We have the input embeddings, and now we're going to dive into what this multi-head attention is. And you can see they use it in a few different places within the overall model. And remember, like this little box here is really 6 of those boxes stacked on top of each other. So what is attention and why is it all we need? So in natural language processing, we talked about how words can be represented as vectors, but also words can mean different things in different contexts. A word embedding holds a lot of information about a word, but depending on the context, you can shift the meaning of it. I think a great example of this is the word fly. It can mean fly an airplane, or that fly is an annoying bug. And in one case, it's a noun. In another case, it's a verb, and have completely different meanings depending on the sentence. I found a pretty fun little visualizer for this here to drive home this point. And so on the x-axis, you can pick 2 words, and on the y-axis, you can pick 2 words. And so I picked like good and bad and bug and action. And you can see that like spiders are closer to bug than action and closer to being a bad bug than a good bug. Butterflies are kind of more on the good side and low on the bug side, but I think that might be because you can have that's like a motion also. But fly is much closer to an action than a bug, which makes sense because it's probably more used in the context of fly between A and Z, and fly is also fly. So it's probably used as an action more than it is as a noun. And so what attention really does is it looks at different parts of the sentence to shift the representation of the words accordingly. So I found this cool little demo that I'll find a link to and put into here afterwards, but I put in the sentence, "You can fly from LA to New York while a fly buzzes around your head in the plane." And so I highlighted fly the first time to see what it was looking at within the sentence. And you can see it's really focused on some of these words around it, like you can fly, because can and fly next to each other really put it into that verb context. And it also is looking all the way down at the bottom to the fact that saying fly a plane. And then if you look at the noun version of fly, it's really paying attention to like the words a and buzz, because for nouns, if you have like a preposition like a before it, it's probably more noun-like. And then, so I thought that was pretty interesting. Yeah, the tool is, I'm sorry, I didn't put a link to it here, but I will put a link to it in the blog post after. It's a fun, I think it's called BertViz, actually. If you just BertViz.
Also, what's the like colored representation? Is that like they've reduced it into a certain number of dimensions, or like what are those doing?
Yeah, exactly. So we can't, so these were like glove word embeddings that are 756 in length. So they're kind of bucketing it to make it easier to see. Cool. Good question. So that's why we need attention, is because you kind of have to look at the context of the whole sentence to really understand what that particular word is. Thank you. Ping put the link in here. Here we go. And if we go back to this example, where I was saying we have a new intermediate representation of the words, the attention mechanism is taking the original word embedding, projecting it into the new space so that the word fly here would be closer to its actual noun meaning or its verb meaning before we feed it into the decoder. So how does it do that at all? We're still kind of hand wavy on the actual attention mechanism itself. So what it really comes down to is these queries, keys, and values. And you'll hear this over and over again as attention being described as mapping a query and a set of key value pairs to an output. And so I found this blog post really great to help. Oops. That's not what I wanted to do. This blog post was helpful to visualize some of these things. And so for each word vector in the input, we have output corresponding query, key, and value vector. So you can see like maybe this is the word law and this is the word quise, and for each one of those we have a weight matrix that we're learning, and a weight called the query weights, a weight matrix called the key weights, and a weight matrix called the value weights. And we're going to multiply each word by these matrices to get a new vector representation out, a query vector representation, a key vector representation, and a value vector representation. The names key, query, and value are inspired by information retrieval systems, where you might have a query as user input, and then you have to use it to scan a bunch of items keys and select an item, a value. So in our example above, when we're looking at the word fly, that would be the query, and then we're scanning all of the words in the sentence, which are the keys, and we're selecting the one that affects it the most, the value. So like in our example above, can fly would be one of the more important values that comes out of there. Another analogy that I've heard is like, you can imagine you're in a grocery aisle and you have a recipe with a bunch of ingredients on it, and the ingredients might be like the words that you're looking for. So each ingredient is a query, each item on the shelf is a key, and when you finally select the item that matches what's on your recipe, you select that as the value. So that's kind of just high level where that terminology comes from. And so attention does this, where it can take a query and find the most pertinent other words to it through a process called scaled dot product. And so this is very deeply within this multi-head attention section. We'll get into what multi-head means, but this is just like one of the heads. And basically what you do is you take the query vector and the key vector and you multiply them together. Then you scale them and run them through a softmax. And the softmax, if you're familiar with softmaxes, are just to like pick an index in another set of things. So the softmax is used to look into the value matrix and pick the ones that it thinks are most important. So this blog post that I mentioned before, Illustrated Transformer, shows this pretty nicely as well. So you might have the word thinking, you have the embedding for it, you have the query vector, the key vector, and the value vector. You take the query and the key that you're looking at and multiply them together. You normalize them, you run them through a softmax, and then you have all of the values on the other side, and you're trying to select like which one of these words is most important. And so that final step of multiplying the softmax by the value matrix will give you a new output word embedding. In this case, they're calling it Z, but all these steps kind of lead up to this new word vector that has a brand new meaning in the context of the words around it. So I'll pause there for any questions, because I think this is the most complicated part and might be the most confusing. They are pretty much just like adds and multiplications once you get down to the bottom. And I think that's why mechanistic interpretability is pretty cool, because like there are studies on going down to these actual embeddings and how the information gets passed between them. And each individual concept isn't that complicated, but as you bubble it up, it gets more and more complicated. So we've talked about, oh, Scott, good question.
There's a question in the chat.
How did it decide to divide by 8? Oh, so yeah, in this example, you're dividing by how many dimensions you have, or that might be the sequence length. That's a good question. It's either the number of dimensions or the sequence length, so you're trying to normalize it across the whole set of values. Cool. So this process that we're looking at is like a single head of attention. You'll notice in the diagram, they call it multi-head attention. So if you did this once, you might be reducing how much information processing each one of these weight matrices can do, or how much decision making they can do. So what this means in practice is that, or people theorize that one layer of attention might get really good at grammar or parts of speech, but lack the ability to disambiguate names from places, because names and places are both like nouns. So you might have one set of weights that's getting really good at grammar and one set of weights that's getting really good at distinguishing George Washington from Washington, D.C., and being able to split out those problem-solving abilities into multiple attention models is what they call multi-head attention. Yes, Ben?
Sorry if I'm unintentionally spoiling the mechanistic interpretability bit, but this does remind me a lot of what they talk about in the literature around computer vision, where you're talking about, as you get deeper into the network, you're learning higher and higher level features. The first layer might be learning just like edges, and the later is like, composing whole forms. But it feels like in vision, we've kind of been able to demonstrate that by peeking into the layers and kind of like messing with the activations there. Is that purely theoretical at this point on the language side, or is that going to be some of the stuff that we get to?
That is definitely some of the stuff that people are trying to poke into, and taking like word vectors and seeing what the activations come out as in different sections of the multi-head attention, and trying to prove that like this head is really looking at grammar versus this head is really looking at disambiguation or something like that.
Yes.
I think it's a little harder to do in language because you don't have the visual representation.
Yeah, totally.
So what this looks like in practice is you really have that same mechanism that I showed above, but you just duplicate it n times. For example, this model, they use 8 of these things, 8 attention heads, each with a dimension of 64. And then they concatenate all of the attention heads together at the end here and run it through a final linear layer. Also, another way that they say the same thing is like they call this attending to different information from different representation subspaces, and claim that the single attention head would have a hard time attending to all the information present. So like maybe one attention head is looking at the female properties of the cat word vector or whatever, or the feline, sorry. And I also thought it was fun to like dive into Andre Karpathy's nano GPT code a little bit here. And you can see he even documented different configurations that you might have here for like GPT-2, a larger GPT, GPT-2 XL. And these are even different from the 8 attention heads and dimension of 64 for each one of the layers within it. You can see these GPT-2 models get even bigger than the attention is all you need one. So yeah, Ben.
That question, Greg. Didn't know if you said.
Oh, how do they direct each attention head to focus on different properties? Yeah, that's a great question. This is something that they don't do explicitly, but they're proposing that the model learns as you feed it lots and lots of data. So these are just kind of, I don't know how you say, proposals of why they think splitting up is a good idea, but in practice, people are starting to dive into like this mechanistic interpretability to figure out if that is actually the case. And Paul said it feels like the difference is that multi-layer with vision, the layers are stacked, but with multi-head, they're sort of peers running in parallel here. And totally, that's true. You can see they're more like parallel processes here, but also they do get stacked on top of each other, as we can see here. So it's kind of like you go wide and you go deep in this sense. And I think going deep in natural language is more like, since we're working with sub tokens and sub phrases, being able to combine those together into higher level meanings is really important. And they actually do a little bit of this later in the paper with dependency or constituent parsing. And I realize this is a long paper, so we're already running up on the 40-minute mark, but attention is used in a few different ways. And so we were looking at like just this little block in here for attending to the sentence itself, but attention is also used as a way of communicating from the encoder to the decoder. So the decoder pays attention to everything in the encoder as well as everything that it's already generated. So they call that like encoder-decoder attention when you're passing information between the two, and then self-attention when you're looking at the either values that you're encoding or like the values that you've generated so far. There's feed-forward networks on top of each one of these attention networks. So again, another component on top of here. These are pretty standard neural network techniques, so probably don't need to dive into much there, but there's a lot of room to play if you wanted to tweak models within there. And then I think the last kind of important piece are these positional encodings. Yeah, Scott.
Another question in the chat for you.
Can you briefly explain the role of the feed-forward network in the diagram? Yeah, so when you do the self-attention mechanism and you concatenate all of the outputs of them, they add these linear layers on top to kind of collate and take all of the information and process it further to make more decisions about it. So it's kind of like a mechanism to get all of that information into one vector, and then you can also start to compress it as you build more linear layers on top of each other, depending on the size of your linear layers. So it kind of just gives the model more room to decide what it wants to do later on. They happen to put 2 layers here. I could imagine you could make that even deeper. You could make that wider. You could play around a lot there. So zooming back in to the bottom, if you remember, we take the input embeddings and there's kind of like this positional encoding step that they do. And they say, since there's no recurrence and there's no convolution, they need some way of injecting information about where each token is within the sentence relative to all of the other ones, because you can run all of these computations in parallel. So for each word, you could independently run it against the weight matrix for the query, the key, and the value, and there's no inherent sense of order there. So they do this with sine or cosine functions of different frequencies. Again, our illustrated transformer blog post was really helpful for visualizing this. And basically, you take that input embedding here, you add the positional encoding to it, and then you get an embedding with positional encoding together. And what the kind of positional encoding looks like itself is, if you're familiar with like a sine or cosine function, it kind of goes up and down like this. And what this is visualizing is this would be the positional encoding for position 0. This would be the vector for position 1. This would be the vector for position 2. And you can see you're progressively increasing the values like at the start of the vector here to say, hey, I'm at the start of the sentence. I'm a little further in the sentence. I'm even further in the sentence. And this is one of the reasons that if you hear, oh, a transformer only has a context length of X, part of that is the type of positional encodings they use. A like sine or cosine function can only really differentiate between a certain number of positions, and two, the context like is dependent on how many sentences the network's even seen with a length of that. So if all the data in the translation data set is like sentences of 100 words or less, it's never going to learn what to do with words that are outside that positional encoding. And also it's just expensive to do the n by n computations. And while it is expensive, it is more efficient than an RNN or a CNN. So I remember looking at all of this stuff and I was like, well, this is still computationally like you're looking at the sequence length by the sequence length and comparing that over and over again. So it is n squared computations. And they just compare that to the convolutional or the recurrent networks. And three things they take into account are the total computation of each layer, the amount of computation that can be parallelized, and then the path length between each of the long range dependencies. So for a recurrent neural network, you're actually, you have n sequential operations that you have to process the first one before the second one, before the third one, before the fourth one. And you also have the dimensionality squared in each recurrent step. And then you also have to hold all of that information at each step to pass along to the next step. So like passing information from the first word to the 10th word requires 10 steps to maintain that information. And that's what this maximum path length is. So if you compare a self-attention to a recurrent network, you have pretty much the same complexity within the layer, depending on what n is and depending on what d is. N is usually much smaller than d because it's like the sequence length of the input, not the dimensionality of the neural network. But with self-attention, you can do all of the operations in parallel. You're not required to do it in sequence. And each word is connected to each other word. So it's just like a path length of 1 between them. So it's more efficient than the recurrent one and passes information faster. Convolutional, you kind of have kernel by the sequence length, by the number of dimensions. And depending on the size of your kernel, to pass information from one layer to another layer, you kind of have to like stack the layers on top of each other. And I think that's probably a little too complicated to get into right now, but convolutional layers, you can think of like how big the kernel is and how many layers you have stacked on top of each other, and that's how you can pass information from one to the other. Finally, they trained this model on English to German data set with 4.5 million sentence pairs. What that looks like is just like a bunch of, well, this is an English to Spanish data set, but a bunch of sentences in English, a bunch of sentences in whatever the output target language is. We have some of this data to play with at Oxen if you want to take a look at it. And what they said was it took, for their base model, it took like 12 hours to train the model on, I forget how many sentences it was, like a much smaller subset of the sentences. And then it took 3.5 days to like really get state-of-the-art accuracy for these things. They did a lot of variations of all of the different parameters and all the different model sizes that I'll let you dive into on your own. And then they also applied this to English constituency parsing, which is a much more structured task of like breaking down a sentence into nouns, verbs, and then noun phrases and verb phrases, and progressively building that up. So like the book might be a noun phrase, but then Sandy likes the book might be a whole sub sentence, and then Sam thinks Sandy likes the book is like the sub sentence. And they showed that these networks were very good at, because they had that attention mechanism where it could reference Sam and the book and pass that information at the same time. It was like really good at this constituent parsing task, which is pretty interesting because like this was a key task subfield of natural language processing just to do this step. And the fact that a transformer could do something as complicated as constituency parsing as well as translation was a key insight of like, oh, what if we just unleash this on all the tasks at once, which we saw and have seen later and later in the research. So, oops, at the end of the day, they introduced this transformer. It's a sequence-to-sequence model based entirely on intention, where they get rid of the convolutions, they get rid of the recurrence. They say that the transformers can be trained significantly faster than RNNs and CNNs, had state-of-the-art performance, and they even mention at the end of the paper that these models could extend well to images, audio, or video, which we're definitely seeing more and more of today. But again, this was like 6 years ago, so pretty cool to see all the variations that have been built afterwards. Scott, do you have is that a hand raised still?
No.
Your arm get tired?
It's impressive how long you're holding it up. Does anyone have any questions before we hop off the video? Happy to hop off and just jam for like 10 minutes if you guys want to. Cool. I'm going to stop the video then.